Hello everyone again, and thank you for joining my presentation. Today we will talk about interesting topic, a state of Java elasticity, how you can benefit from the recent Java improvements and actually how it works. The session can be helpful for people with no knowledge and with advanced knowledge. So we will discuss basic things and we will also touch some practical points. A little bit about myself. I am co-founder and CEO of Elastic Platform as a Service. I'm also a Java champion and creator of 2 products that won Duke Choice Award. I'm deeply involved in development of cloud computing technologies and participate in Java community actively as well. Specifically focusing in vertical scaling of Java and Java elasticity. So this is the reason why I'm speaking about elasticity in general. And today we will talk about problems. So what exactly problems we have and how we can solve them, about use cases when it's useful to have Java elasticity. Also, we will cover recent improvements in OpenJDK, what practical examples, how it can be used for your applications. Also, analyzing vertical scaling inside virtual machines and containers, because there is a big difference between these two. As well as walk through some testing results with different garbage collectors, and a little bit information about upcoming improvements in OpenJDK related to Java elasticity. So if you're ready, let's start from the problem. One more. So what is the problem? There is a good example how JVM consumes RAM in most cases. So orange line, it means committed heap. So red line, it's max heap. It's maximum heap to which Java can grow. Let's say, right, JVM can grow. Orange one, it's committed. So when JVM said to operating system, I need this RAM. I will use this RAM for my own needs, for my objects. So operating system reserved this RAM specifically for Java process. And blue one, it's a real used heap. So when real objects use memory. And as you can see, the difference between real used and committed reserved heap, it can be huge, right? So very often Java can grow up, but it does not release resources back to operating system. So it just holds these resources. And it becomes problem because if you scale your application, like if you have multiple containers, many instances, this inefficiency grows together with number of your Java instances. So that became, let's say, inconvenient problem, and it became even more obvious. The problem exists after people realized power of microservices, right? And after they started to put each JVM inside a dedicated container or even inside a dedicated virtual machine, right? But they place one application per one JVM, or very often one application on top of multiple JVMs, right? In the past, it was a little bit different approach when Java just started. In many cases, people put multiple applications inside the same Java virtual machine. So this memory issue, if it's underutilized by one application, then it might be utilized by another application. This memory issue was not so big, let's say, people did not pay so much attention. But as soon as, again, like as you put each application inside dedicated, isolated virtual machine, and if this virtual machine holds the RAM that is not used by application, inefficiency grows significantly. So you lose money from underutilization of your infrastructure. In other words, in simple words, you pay for resources that you don't use. And we can find many questions in the internet, specifically at Stack Overflow, right? People ask how to return memory back to operating system from JVM. And also there is interesting confirmation from Jakarta EE community. They did a survey in 2018 about the most challenging aspects while working with Java EE. and large memory requirements was named as #1 issue, actually. So it's like about 40% of respondents mentioned this problem. And what are the use cases? What are the reasons to seek for Java elasticity? Which workloads can benefit from this? Few examples, just let's say simple example with desktop applications with IDEs. When you have your IDE, right, and you build some software and you compile it, and the IDE can get RAM from operating system, but at some point the task is finished. And if your IDE keeps holding the RAM, so your computer will become slower during the time, right? And not during the build time, let's say, during the whole period of time after the build, which is not convenient. So it's better to return unused memory back to operating system. So next example, dynamic stateful workloads. So for example, if a workload should stay as long as possible, and at some period, for example, more load came to the same instance, and you need to get a little bit more power to handle this load without errors. So if you have elasticity, if you have vertical scaling, you will be able to just to get a little bit more resources to the same instance, and the problem will be solved. But if there is no elasticity, complexity of handling such cases is growing significantly. So you need to set up another instance for horizontal scaling, distribute the load, or you have to stop the workload, right? Increase the limits and start it again. So like it will take time, and it will put additional load on the disk probably, right? Because you will read again all the data to put inside the memory. Good. Another example is scheduled tasks, jobs, for example, for data processing. It might happen that like you do periodical data processing, right, during the nights, some data aggregation or segregation. And so during this time, usually RAM gets busy. But when the tasks are finished, it's good to return this RAM back, so this RAM can be used by other processes and system becomes more efficient. Also, right sizing problem is very important to put right sizes of your instances in the cloud, because, for example, if you put less, your application will face performance degradation issues, right? If you put bigger limits, then probably you will pay for resources you don't need. So it's very important to have, first of all, right sizing for fixed workloads, and have elasticity and vertical scaling for variable loads. So, and also the case I like the most, elasticity brings opportunities for new billing models, more efficient, more cost efficient for end customers, when end customers pay only for what they use, not for the limits for potential scaling. So these cases all benefit from Java elasticity. But to be able to configure Java properly, Java virtual machine properly, we need to understand its footprint, where JVM keeps resources, right? So there are three major areas, let's say. Some data are stored as shared native libraries. Some memory consumed by thread stacks. Also, the most widely known part is heap, where Java puts objects of your application, right? And then there is additional area which we call like native memory, where JVM keeps internal data, internal structure, code cache, and direct by buffer classes allocate objects directly in native memory. So you need to properly configure each of this layer, and to be able to figure out what is the maximum memory your Java process can consume. So there is a formula which explains how it works. So how to calculate. Yeah, let me show you. So there are 4 areas. First of all, XSS, amount of, let's say, memory allocated per each thread inside your JVM, created by your JVM. So then second area is heap XMX, right, where you store your objects, your application objects, and then metaspace, some internal data of JVM, and max direct memory size, where you can store object as well, but directly in native memory outside of heap, right? So, and configuring properly each this parameter is important for a stable work of your JVM. I'm not talking even about scalability, about stable work of your JVM, because if you configure it wrong, in the wrong way, you might face issues. As I mentioned, one of them, it can be performance degradation, and another one can be over allocation of resources. So you overpay for unused resources. So it's very important and very beneficial, let's say, to put maximum memory usage limits very close to the limits of your virtual machine or container. So not higher, not less. So the most optimal is as close as possible. Of course, you need to leave some memory for operating system needs, but we will keep it outside of this talk, just focusing today only on JVM. So what kind of problems might happen if you configure in the wrong way your JVM? So the most widely used, not used, I mean faced, when people face the most often issue when out of memory happens inside the heap size, right? So you put wrong heap size at the beginning, so you underestimated the load, yeah, like, or you just load came accidentally, so you didn't expect this load or amount of data you will process by your application. So what happens when used memory by objects go close to XMX heap limits, right? And JVM cannot allocate any more memory space for objects. So JVM throws out of memory exception. And there are different kinds of Java memory out of memory error. By the description, you can understand where is the entry point for you to take a look. Is it heap? Is it metaspace? Or maybe it's related to threads stack. So it can give you some initial understanding, but you will have to go deeper and analyze what the problem, what the problem exactly is. And another case, when you misconfigure your JVM inside virtual machine or container, when, for example, JVM itself requests more memory than it's available for a container or for virtual machine. So in this case, out of memory exception will happen. Sorry, out of memory kill event will happen. Operating system will kill your JVM instance, and you will lose all data. I consider this case is even worse comparing to the previous one when out of memory exception happens, because in that case you lose only part of the data. When out of memory kill happens, you lose all data inside. So if your application is stateless, maybe it's not a problem. And very often people solve the issue by just restarting the JVM process, right? But it's masking the problem. It does not solve the problem. So it's, I would say, like restarting container automatically when it happens. It's some kind of workaround, but in reality, it doesn't solve the problem. It's better to find proper configuration or to enable elasticity. So to avoid out of memory kills. Good, and let's take a look again deeper inside the problem. So what happens inside heap? We were focusing specifically on heap. I mean, like my team and people from other companies, we joined together and did some research how we can improve elasticity of Java memory heap usage. And again, speaking about the problem in the past, Java can grow up quite quickly, get memory from operating system, but it will never return it back. It happened in many cases. So Java just keeps consuming the RAM and the system becomes inefficient. Some garbage collectors allow it to shrink the unused heap to return this unused memory back to operating system, specifically, for example, G1 garbage collector. But it requires explicit call of full garbage collection cycle. So you have to explicitly call from your Java application full GC, which is not the best case because, as we know, stop the world will happen, right? Java will have to stop and collect garbage and release this garbage. But anyway, at least we had some workaround in the past, right? And our work was focused on how we can improve the situation, how we can make it fully automatic when Java understands that unused memory is not needed anymore and it can be returned back to operating system. So we created a patch specifically for OpenJDK. So it's publicly available. There is a link to this, the description of this patch, but in short, what it does. So it introduces 3 parameters. First of all, one of them says that please call periodic garbage collection cycles. So you specify interval after which garbage collection cycle will be called. So then second parameter helps you to avoid calling garbage collection cycles when system load is high. So it's some kind of threshold. You specify threshold. For example, you say like, okay, please don't call full garbage collection. Just don't call garbage collection cycle if load is higher than specific number, right? So it's useful when, for example, CPU is busy, when system is busy, and you don't want to have any elasticity during this time. So you just specify the threshold. And another parameter that regulates what kind of garbage collection cycle should be called, full garbage collection cycle or parallel, concurrent garbage collection cycle. Yeah. Concurrent garbage collection cycle does not introduce stop the world. So it's more preferable to use this kind of garbage collection. But if it doesn't work for your application, so you can switch off because it's enabled by default. So you just write here, sorry, minus, and full garbage collection cycle will be called instead of concurrent. So great, and there is an example how to add these parameters to your Java application. Again, it works specifically for G1 garbage collector. It was introduced specifically for this kind of garbage collection algorithm. So, and there is an example how you can specify it. Please pay attention, it's available only from Java 12. We are talking with the community about backporting this back to Java 11 because we see great benefits. And unfortunately, migration from older versions to newest versions of Java is not happening fast. So we will see, maybe we will have this in early versions as well. But from Java 12, you can easily add additional parameters and enable elasticity, enable automatic shrinking of your Java virtual machine. How it will work. As an example, this chart explains how automatic release of unused memory works. So Java memory consumption grows up, and when it stays a little bit, and when it's not needed anymore, and orange lines goes down again. So it can be very flexible. And after we introduced this patch, Java community realized, let's say, our achievement, recognized our achievement, and we won Duke Choice Award. We are thankful for this, of course. It motivates us to put even more efforts. And before this patch that was introduced in OpenJDK, how we get to this point? We did many tests with our own agent, so we use some kind of workaround by attaching our Java agent that controls current usage of memory. And if there is enough memory to release, if there is some memory to release, I mean some committed memory but not used memory, this agent will call full garbage collection cycle. And this is available by default for in our product in Elastic for Java users. For any Java applications with JDK lower than 12, because after 12 version we use the recently introduced patch. But also if you need elasticity and you cannot use Java 12 and you don't use Elastic, let's say, you can go to this repository in GitHub, and download this agent and just connect this agent to your application in this way. And that's it. So you will get the elasticity as well. It's not hard, but again, like it requires some extra configuration. Plus, you need to take into account that full garbage collection cycle will be called. You need to take a look. You need to pay attention if this does not bring performance degradation for your application. So don't put it on productions. Start from dev test environments first of all. But with this patch, again, like I believe it's quite safe to put it on production. Moreover, we have periodic system loads threshold where you can specify specific limits. Do not call elasticity if system is busy at this moment. Great. So, and how it looks when this workaround is applied is pretty elastic as well. As you can see, it grows up, right? And at some point, full garbage collection cycle is called because these agents found unused but committed RAM, and then RAM goes down. It works again only for G1 garbage collector. Great. Practical examples. For example, with Jenkins, Jenkins. It's quite popular continuous integration, continuous delivery tool used by many projects around the world. Simple example. So left side kills this. When we run Jenkins with Elastic garbage collection agent, and right side without garbage collection agent. The initial parameters we have the following: container limits 8 GB, max heap limit 6.5 GB, right? And then when we launch Jenkins, we just do simple sign-in action, like simple login action. Memory consumption goes up. So from less than 1 GB, more than 3 GB. So just only after you sign in to Jenkins. And when after some time, our agent realizes, okay, this memory is not needed anymore, and it releases memory and returns back to operating system. So we did the same test, but just removed this agent. And as you can see, after login action, memory consumption goes up, but it never goes down. So it just keeps the RAM. It cannot be shared with others. So and you will have to pay for this resources. That's the problem we have, but again, like fortunately, we have these improvements now, and it's possible to fine-tune your JVM and make it very efficient and very elastic. In addition to Java elasticity, it's also important to take into account in which virtualization environment your Java process is running, because there is a big difference if you run inside virtual machines and containers. So let's take a look at this difference, but before we go and check the difference, let's discuss basic things like what are the benefits of vertical scaling in general, right? So first of all, it's much easier to deploy and configure, and it is the fastest way to boost performance, right? Like it's much, because there is no network delays between the instances and all the resources available to the same application, to the same instance, and it's much easier to scale up because you don't need to change your code. You don't need to redesign the code. There is no need to synchronize data. So it's much simpler, let's say, right? Of course, it can be more cost efficient it helps to get the best cost efficiency, let's say, because without vertical scaling, you will always have over allocation and overpayment. And another good point, today, large memory instances are available in many cloud vendors. So scaling limits is quite high, like 10x, 20x. It's very good. So today, vertical scaling is much more powerful than, let's say, 5-10 years ago. Of course, it doesn't solve all problems. It cannot replace horizontal scaling at all because there is no high availability. It's much harder to implement zero downtime upgrades without horizontal scaling. Yeah, so only vertical scaling itself, while it's useful for many workloads, but in combination with horizontal scaling, it brings the most benefits. So if you know how to scale application in both vectors, horizontally and vertically, you can achieve the best results. Let's analyze how, let's say, vertical scaling works inside virtual machines. Let's imagine this green one is resources used by our JVM, right? And of course, we set limits higher than JVM consumes. Just in case if more load comes, our JVM has a little bit more space to grow up. Modern workloads are variable. It's not, it's very often today, let's say, that the load goes up and down because people are searching something during the day, in the internet, during the night they sleep, right? So our workload is variable. And it's the same happens inside virtual machines. Java process goes up and down, but due to specific how a virtual machine works, the resources limits that allocated to your virtual machine, in the most cases, these resources are reserved. So, and cannot be shared with other virtual machines on the same host, right? And this is the reason why all cloud vendors, infrastructure as a service cloud vendors, they charge you for the limits because they say that it's allocated to your virtual machine. They don't care if you don't utilize fully these resources. You always pay for the limits. So that's one of the big differences. If your Java application is elastic and super scalable, right? But if it works inside virtual machine, you may lose some benefits of elasticity. Because again, like your virtual machine should be as elastic as your workload. If we talk about containers and say JVM, for example, runs inside container, containers by default, they share unused resources with other containers on the same host. It's a built-in feature, so you don't need to do anything else because it's like done by default by Linux kernel. So all unused resources will be shared to other containers. So it means with smart algorithms, you can put much more workloads and you can utilize the infrastructure in a better way and make it more elastic if you run Java inside containers. Also scaling virtual machines and containers vertically, increasing, adding more resources to the same instance is different. For example, in virtual machines, it's even in the most cases impossible to add more resources to the same instance. If we are talking about public clouds, for example, right? Like you buy like 4 GB of RAM at the beginning, you realize it's not enough for your Java application. You have to buy another virtual machine and migrate to another virtual machine. You cannot add resources to the same instance with virtual machines. I'm talking about public cloud in the most cases. Of course, in private cloud, there is a possibility to add more resources to virtual machine. Sorry. But also another important point, when you scale up, when you buy bigger machine, you cannot buy it just a little bit bigger. You have to buy it twice bigger in the most cases. Cloud vendors offer you a very specific predefined instances. So you can scale only by just paying twice more. So if your application needs a little bit more, you have to buy twice more resources. Again, your problem of underutilization of unused resources, overpayment for unused resources is growing up. With containers, it can be different again because containers are more elastic by default, by design. It does not require extra efforts from vendors to change the limits on the fly. It's very easy and fast way. Containers can be adjusted without restart of the container. So you can get more resources to the same container. Not every vendor offers this. Some vendors force you to use stateless workloads, right? So they will be able to restart container at any time they want. But please keep in mind there are also stateful containers, and the possibility to scale your container vertically is more advanced comparing to scaling virtual machines vertically. How it works from, let's say, cloud hosting service provider point of view, right? Like this vertical scaling, like where resources gets and how they are shared between other containers. So let's imagine the case we have like large host machine, right? And we run multiple containers on top of this host machine. And at some point, one container needs more resources. So it just gets these resources from available pool on this host machine. Usually, like cloud hosting service providers, they keep like 20% pool, like a 30% pool of available resources, just in case if one of the containers or few of them will need these resources. But after job is done, the container returns this memory back to pool of resources. So, and these resources can be used by another container, right? And when this container doesn't need the resource, it gives this back. This opportunity and this functionality enables, unlocks introduction of a new, more fair billing model for end customers, which is called pay-per-use, right? When you pay for only real resources, and cost of available pool resources in the pool will be on cloud service provider side. With traditional model today, like we have pay as you go, when we pay always for the limits, this available pool of resources is, let's say, split between each virtual machine. So it's located inside each virtual machine. So, and this is the reason why cloud hosting service provider puts the cost of this spare resources, let's say unused resources, to end customers, right? Because they don't manage this in the most cases. Yeah, and introducing pay-per-use model solves right sizing problem. You don't need to guess in advance how much limits you need to allocate. Okay, and how it works, for example, inside Elastic, we have simple slider, right? And people can just drag the slider and set high limits. They're very easy, let's say, with this limit change, because you know, like they don't afraid they put more than they will consume. These resources are not really charged at the end, so they can put higher scaling limits. And we did interesting research. We tested, we collected statistics from multiple customers, multiple cloud service providers, and compared scaling limits and real used resources during the time. And you can see people in reality put much higher limits than their applications consumes. So, and if we go with old business model, I mean billing model, pay for the limits, it will be more expensive for end users, right? So pay-per-use brings significant benefits today. And then let's talk a little bit about testing of garbage collection inside different garbage collectors, let's say. So there is a simple test. We create a linked list and stuff this list with string array. Just do loop and put string arrays inside this list and do some sleep. The source code is available on the GitHub. It's pretty simple application for vertical scaling. You can test your environments by this application, how they are scalable. And what we have different garbage collectors that we will run inside containers, inside dedicated containers, and we will run load test and see how they behave. So First of all, G1 is default one today, and it's scalable one now. As you can see, it can go up and down. It's very useful. And another one I would like to highlight, Shenandoah. It's a new generation garbage collection algorithm introduced by Red Hat, and it's scalable by default as well. So it's very elastic, and I like it very much. There is a new one, ZGC garbage collector introduced by Oracle. This garbage collector is elastic as well. So Oracle, let's say, understands the importance of elasticity, right? So they added elasticity to their implementation as well. C1 from, or sorry, C4 from Azul Systems, commercial implementation of Java Virtual Machine. Actually, this implementation exists for a long time. It's scalable as well, but it's commercial one. So if you use Zinc, please take a look at this opportunity. So you might save a significant amount of resources. Sorry. And deprecated garbage collectors, concurrent mark sweep. It can be scalable, but you have to call full garbage collection cycle. You have to force full garbage collection cycle and call it 4 times to bring it down at all. Yeah, serial garbage collector, it's scalable as well, but in same way as concurrent mark sweep, you have to call full garbage collection cycle. Then OpenJDK. Actually, this one is good too. It's very cost efficient in terms of memory usage compared to others, and it's scalable vertically as well. But you have to check it in a specific way. The implementation is a little bit different. I'm still testing this OpenJDK, trying to collect a little bit more understanding how it works. But again, like from first look, it sounds like it's scalable vertically well. It's just a little bit different implementation and a little bit different measurement of real used resources. Okay, and parallel garbage collector, if you use this parallel garbage collector, it's not scalable vertically at all. Most likely you will have over allocation problem and underutilization. So please consider migrating to new modern garbage collectors. Great, great. And the main points to understand while you are configuring your vertical scaling. So there are, let's say, 6 points, right? Point A, initial usage. So what is the initial usage when your application starts? Then B, what is the maximum usage can happen during lifetime of your application? Then C, what is the speed growth from initial usage to maximum usage, right? So how fast it grows, because different garbage collectors, the speed of growth, the speed of memory allocation can be different. So one of them performs better than others. So if your application is sensitive and scale range is big and it must scale very fast, so I think you will need to analyze which garbage collector fits better for you. Also D, how long, let's say, object stays in memory, like do they stay for forever, like, or they stay like short period of time? So if they stay short period of time, then let's say next comes is E, release point, sorry, duration before it release. Yeah, so we have this when release will happen, yeah, because it might happen the following. Your objects are in RAM, but they are not needed anymore, but your garbage collector is not called, so, and JVM keeps for several hours, right? Or you can configure that memory will be released during like several minutes. So this parameter is configurable and tunable. Again, like it depends what you need. And then release speed, how fast it goes down, and minimum usage after the memory was released. So these points are the key points to consider while configuring your elastic scaling. We also have some tests inside Kubernetes of different garbage collectors. You can download presentations after my session and take a look deeper. We did also testing of Jakarta EE application, specifically implementation, specifically with Glassfish. The test was pretty simple. We created a web page which put GPS page, yeah, GSP, Java server page. And then we set some string array inside session. So we stuff session with objects. We emulate like customers come in and they're, trying to, for example, to buy something, and we put data inside their session on the server. So, and then we call the loop, right? And we emulate load. It's pretty simple load, like very simple and very straightforward, but it helps to understand how vertical scaling works. So you can see with Shenandoah, it goes up and goes down pretty easy. Like after some period of time, JVM just releases unused memory. Yeah, same happens with G1 and serial garbage collector. And with parallel, it just does not work. So if you use the garbage collector parallel, please pay attention. It's not really scalable vertically. Great. So in short, we discussed what we achieved already, how we can test this, and let's talk a little bit about the next upcoming possible improvements. First of all, what we want to improve also, we want to be able to resize XMX in runtime, because we hear many requests related to this functionality. It will help again, like to adjust wrong configurations, wrong guessing. Let's say if you configured system accidentally in the wrong way, it will be possible to adjust configurations on the fly without the need to restart your virtual machine. Also, it opens up new opportunities for more advanced algorithms, including adaptive performance optimization, right? When systems will be able to automatically adjust these limits. So what steps we have in this direction? Oracle introduced softmax heap size in their ZGC garbage collector. So what it means, it's some kind of emulation of XMX resizing, but different way a little bit. So you can set second limit, let's say, before XMX, right? And application will try, JVM will try to keep memory usage lower than your softmax heap size limit. And this limit is manageable, so you can change this in runtime mode. It means like if it's not working well for you at the beginning, you can adjust this limit. The only point here that if it's impossible to keep memory usage below softmax heap size, JVM will allow memory grow higher this limit. So you will go higher this limit, but till XMX, till maximum heap size. Yeah. And then JVM will try to, again, like to bring it back lower than softmax heap size. I believe this is useful new functionality, new option, which can be helpful for many projects and use cases. Same actually, softmax heap size functionality is introduced in Shenandoah and in G1. So it's not available yet, but the work is going on this. So we will have more or less similar implementation across several garbage collectors. Same functionality exists in OpenJDK. It's again implemented in different way, but the idea is pretty the same. And yeah, like it's pretty same approach can be configured inside Zinc system tools, JVM, commercial JVM created by other systems. So yeah, and in addition, there is ongoing work right now for improving elasticity of metaspace. If you remember, we discussed different areas, right? Like so, we fixed elasticity for heap for XMX. Now the work is going on this here, like in max metaspace size, and also recently direct memory algorithms were improved improved as well. So I believe Elasticity was improved in this area as well too. So as you can see, the topic of elasticity came across all major points of JVM. Yeah, and Java became much more elastic, more cost efficient, and more scalable. So which is great. And that's it in short. I hope my presentation was useful for you. If you have any questions, feel free to follow up me in social media, or if you have memory consumption issues. So we have specific emergency team who can help you to find out the root of the problem, to find out how big is this problem, first of all, right? We analyzed thousands of containers, Java running inside containers. So if you have any consumption issue, feel free to ping me and or send message to savememory@jelastic.com. And we will help you to get better efficiency, to make Java more elastic, and you will help Java community to get a better Java and to more elastic Java, because again, like, we contribute our work back to OpenJDK. So thank you very much. Now coming back to studio.